Stop ruining expensive 12-volt batteries with raw solar power. Connecting a panel straight to a battery will destroy it, either by overcharging it during the day or completely draining it overnight. To build a reliable off-grid system, you need automatic overcharge and deep discharge protection. Let's break down this complete charge controller circuit, step by step, using a detailed 3D animation. Here is the full schematic diagram of the circuit that solves all of these power management problems. Now let's examine the actual physical circuit components in 3D to see how each part is connected and functions in real-world space. Starting right at the solar input connection, the positive rail links directly to the anode of a high-current 6A4 power diode. This diode acts as an electronic one-way check valve. During peak daylight hours, it allows heavy solar current to flow freely forward into the system. But the moment the sun sets, its internal junction becomes reverse biased, completely blocking any stored energy from draining out of the battery and back into the dark solar panel. Moving deeper into the circuit, we reach the core monitoring logic, powered by an LM741 operational amplifier configured as an analog voltage comparator. To give this op-amp a stable baseline to measure against, regardless of battery fluctuations, a 1K current-limiting resistor powers a 1N4732A Zener diode connected in reverse breakdown mode. This Zener diode holds pin 3, the non-inverting input of the op-amp, at a rock-solid fixed reference voltage. To sample the live status of the battery, a 10K multi-turn potentiometer is placed across the battery terminals, creating an adjustable voltage divider that feeds a proportional fraction of the battery's real-time voltage directly into pin 2, the inverting input of the op-amp. Additionally, a 1 meg resistor is tied between the op-amp's output, pin 6. This creates a subtle hysteresis effect, which prevents the circuit from rapidly flickering on and off when the battery voltage hovers right at the switching threshold. The output from pin 6 of the LM741 drives the control network, consisting of the 2N3904 NPN transistor and two IRF540N MOSFETs. The transistor drives the gate of the first IRF540N MOSFET, Q2, whose drain connects to the load line and controls the gate of the second IRF540N MOSFET, Q3. It is this second MOSFET that directly regulates the main charging path to the battery. During active charging, the op-amp output at pin 6 stays high. This high signal lights up the D5 red LED to show that charging is active, while simultaneously turning on the 2N3904 transistor. Turning the transistor on pulls the gate of the first MOSFET, Q2, low to keep it off, which allows the second MOSFET, Q3, to switch on and pass charge current directly into the battery. When the battery reaches full charge, around 14.4 volts, the op-amp output at pin 6 switches low. This low output turns off the D5 red LED and turns off the 2N3904 transistor. As a result, the first MOSFET, Q2, turns on, pulling down the gate of the second MOSFET, Q3, to turn it off and immediately stop charging. Simultaneously, current pathing triggers the D1 green LED to glow, signaling that the battery is fully charged. During daylight operation, while the battery voltage remains below the upper cutoff threshold, the op-amp output at pin 6 stays high. The D5 red LED glows brightly to indicate active charging, and the 2N3904 transistor stays on, keeping the second MOSFET, Q3, fully saturated so solar power flows smoothly into the 12-volt battery. Conversely, if the battery drains near the low discharge threshold, the load circuit isolates to protect against cell damage. Before using your charge controller, you need to calibrate the exact overcharge cutoff voltage. Connect an adjustable DC bench power supply set to your target peak battery voltage, typically 14.4 volts, across the battery terminals. Slowly adjust the 10K potentiometer until the voltage fed into pin 2 of the op-amp just crosses the Zener reference at pin 3. The exact moment it matches, pin 6 drops low, extinguishing the red charging LED and turning on the green full LED. With just an op-amp, 2 MOSFETs, and dual LED indicators, your solar setup is completely automated and calibrated for peak efficiency. If this 3D breakdown helped you understand the circuit, hit that like button, subscribe for more electronics explanations, and drop your questions in the comments below. Thanks for watching.